Dear students, uh, this is in continuation of our previous lectures on organic reaction mechanism. And in the last lecture, we have discussed about carbocations, and the next in this lecture, we will be discussing carbocation rearrangements. And out of these carbocation rearrangements, Wagner Meerwein rearrangement is the most important rearrangement. Carbocation rearrangements, they are extremely common in organic chemistry, and these are defined as the movement of a carbocation from an unstable state to a more stable state uh, by using various structural reorganizations shifts within the molecule. So this is an intramolecular shift which take place in the molecule, wherein what we get first is a carbocation, and that carbocation changes from less stable state to more stable state by this type of alkyl or aryl or hydride shift, and then ultimately we get a product. So we know when SN1 reaction takes place, then carbocations they are formed as the intermediate structures, and once a less stable carbocation is formed, it tries to change into a more stable carbocation. For example, if we see this example, uh, when 3-bromo 2,2-dimethyl-butane reacts with silver nitrate, we get a secondary carbonium ion. And this secondary carbonium ion by 1,2-methyl shift changes into a more stable tertiary carbonium ion. And this on reaction with a nucleophile changes into an alcohol. So alkyl halides, they are ultimately changed into alcohols, but only difference is that the nucleophile gets attached to a carbon other than to which the halogen was attached. So that is why these types of reactions, they are called as rearrangement reactions. And if thermodynamically in terms of energy and reaction rate we see, we can clearly see that energy of the system where secondary carbocation is formed is higher than the energy of the system where tertiary carbocation is formed. So tertiary carbocations, they are more stable than the secondary carbocation. So that is why these types of shifts they take place, and these types of shifts lead to products which we call it that they have been formed by carbocation rearrangements. Then theory of these rearrangements is that these types of rearrangement only occur with cations and not with anions or radicals. So here if you see, this is the vacant p orbital of the carbocation, and this is the adjacent carbon which is having a carbon hydrogen sigma bond, and because of the transfer of electron density from the sigma bond to this vacant p orbital, this type of transition state is created, and ultimately the transfer of this hydride from this carbon to this carbon takes place, and then this carbon will have a vacant p orbital, and this carbocation will be more stable as compared to this carbocation, because here the state of the carbocation has changed. Here it was a secondary carbocation, whereas here it is a tertiary carbocation. So this is how this type of process where a hydride ion interacts with the empty p orbitals of the carbocation. Then the rearrangement will only take place if bonding orbital of the migrating group is coplanar with the carbocation orbital. So they should be in the same plane. Only then such type of transfer will be possible. Otherwise, if they are not in the same plane, then such type of rearrangement reactions, they will not take place. And in cationic rearrangements, two electrons, they are involved in a bonding molecular orbital. So these two electrons present over here, they will be transferred to the adjacent carbon atom, and this carbon then will have a empty p orbital. Then these rearrangements are known to occur by migrating a hydrogen, as we have seen in this example, or there can be shift of methyl group, like alkyl group means methyl, ethyl, or any other group. So alkyl group can also migrate, which we have seen even in the last slide, or aryl groups like phenyl or substituted phenyl, they can also migrate. And when alkyl or aryl group migrate, then that rearrangement is called as Wagner Meerwein rearrangement. And this 1-2 shift is the most common type of rearrangement. So because two electrons are involved, that means these two electrons, they will be present in the bonding molecular orbital. So that is why this will have a lower energy as compared to anti-bonding orbital, where in case of anions or radicals, you require anti-bonding molecular orbital also. So that is why they will be higher in energy, and the rearrangement will occur only with cations, because this is lower in energy. Then as we know that carbocations, they are generally unstable species, and therefore they are the intermediate structures, and because of their unstable nature, they need to be converted into products in a very short span of time. Then they react with some other species to form a stable product. And for example, if we are having, say, this substrate 1-bromo 2,2-dimethyl propane, this reacts with silver nitrate, and this type of primary carbocation is formed. And this primary carbocation, by changing of this methyl group to this group, will be changed into a more stable tertiary carbocation. Now this tertiary carbocation, because this is more stable, this will get converted into a product, and the product formation can take place by two methods. Either it can interact with this is an electrophile, this can interact with some nucleophile to give us a product through unimolecular nucleophilic substitution pattern, and this water will act as a nucleophile and get attached to this carbon, and we will get these types of alcohols as the product. Or one of the hydrogens from this carbon, they will be eliminated through unimolecular elimination mechanism, and we will get these types of alkenes as the product. So what I mean to say is that when the rearrangement has taken place, that is the alkyl shift has taken place, then the intermediate carbocation formed will get converted into product either by nucleophilic substitution or by elimination mechanism. So either we will get an elimination product or we will get a substituted product. Then carbocation rearrangements, they are mainly of these 5 types: Wagner Meerwein rearrangement, then pinacol-pinaclone rearrangement, Tefnew-Damsanov rearrangement, then some acid catalyzed rearrangements of carbonyl compounds. and then anchimeric assistance or neighboring group participation also comes under carbocation rearrangement. And for anchimeric assistance, we have already are having a lecture on YouTube about neighboring group participation or anchimeric assistance. And in this lecture, we will be discussing mainly about Wagner Meerwein rearrangement, and for all other three topics, we will be having another lecture on these three ones. Now, Wagner Meerwein rearrangement, as I have already told you, that whenever there is a shift of alkyl or aryl group, then that type of carbocation rearrangement is known as Wagner Meerwein rearrangement. So, when alcohols they contain more than two alkyl or aryl group on beta carbon, and when they are treated with acid, the product formed is generally a rearranged product through migration of alkyl or aryl group rather than normal substitution or elimination products. So such type of migration of alkyl or aryl group will give us a product which will be called as a rearranged product or abnormal product, and the process that type of process will be known as Wagner Meerwein rearrangement. And the basic theory about the Wagner Meerwein rearrangement is again same. The newly generated carbocation is stabilized generally by loss of a proton to give olefin, and the rearrangement involving migration of methyl group is a special class of Wagner Meerwein rearrangement, and this is called as Nemetkin rearrangement. So any rearrangement where methyl group is involved as a migrating group, that will be a special type of Wagner Meerwein rearrangement, and that will be called as Nemetkin rearrangement. Now, for example, if we are having this camphenylol, this one 3,3-dimethyl 2,2,1 bicycloheptane 2O, and when this is treated with acid, we know this acid will react with the alcohol and water will be eliminated by protonation of this alcohol, and when water will be eliminated, that means a carbocation will be generated like this. Now this carbocation can either remove this proton, or a shift of the methyl group from this place to this place can take place. But if this hydride is shifted to form a carbon-carbon double bond at this place, then the product formed will be a strained product. This type of alkene is not very stable alkene, so that is why this will not go into this direction, that this alkene will not be formed. Instead, this carbocation form will undergo 1,2 methyl shift to give us this secondary carbocation will change into more stable tertiary carbocation, and this tertiary carbocation, then this will lose proton at the beta carbon, then to give us this type of alkene as product. Xanthine will be formed as product, which is not strained and very stable alkene. So that is why here the 1,2 methyl shift has taken place to give us a rearranged product, and this is an example of Wagner Meerwein rearrangement. Then this was discovered by scientists H. Meerwein and G. Wagner, and most of the examples they studied, they were in case of natural products, that is terpenes were their field of discovery of this rearrangement, and some of the examples which they have studied, first is that they studied the addition of gaseous HCl to alpha pinene. So this is a natural product, alpha pinene. When HCl is added to this, so that means HCl will add to this carbon-carbon double bond, and we know that addition of HCl to an alkene is taking place as per Markovnikov rule. So that means negative part will go to the carbon which is having minimum number of hydrogen atoms. So that means negative part is chloride ion that will get attached to this place, and H will go to this carbon, and we will get this type of pinene hydrochloride. And then this pinene hydrochloride loses this chloride ion. uh, Chloride ion is lost, and we will get a carbocation of this type. So this carbocation is formed, is equivalent to this structure. I have given the numbers not according to IUPAC nomenclature, but just to tell you that how the bonds are formed and how this structure is equivalent to the carbocation which we have formed over here. So you can see over here that this bond migrates, bond 1 and 6 migrates to position 2. So that means this 6 gets attached to 2, and it gets detached from position 1. So position 1 will become our carbonium ion. You can see over here that position 1 is carbonium ion, and 2 and 6 they form a carbon-carbon bond, and this structure can be written like this also. One is our carbonium ion, then 2 is this one, 2 is attached to 6 with 2 methyl group, 2 is attached to 6 with these 2 methyl group, and rest of the molecule I have written like that. So this is this carbocation is equivalent to this carbocation, and then this can interact with again with chloride ion at this place, and we will get boronil chloride as the product. So basically you can see that migration of this methylene group has taken place, so alkyl group has taken place. So because of this, this is known as Wagner Meerwein rearrangement. So this is how alpha pinene can be converted into boronil chloride through Wagner Meerwein rearrangement when the reaction is done under ST condition, and acid used here is HCl. Then another example is that camphene. The first example was pinene. This is also a natural product, camphene. And when camphene is reacted with HCl, that means HCl will be added to the carbon-carbon double bond, this one. And again, addition will be as per Markovnikov's rule, and Cl will add to this position, and then this will form a carbocation like we have seen in the previous case. And when carbocation is formed at this place, then again you can see that this is equivalent to this structure. The carbocation is present at position 3. You can see over here. Basically what we have done is that we have taken this upside, this bridge downside, and this has moved to this place. 5 and 6 has moved to this side, this has moved at this place, and this has moved at this place. And you can see over here 3 is having methyl, so this is carbon 3 having methyl group. Then 3 is attached to 2 with 2 methyl group, this is our 2 methyl groups. Then 2 is attached to 1, this one, and then 1 to 7 we have taken it towards this side. this has gone towards that side. So this is 7, and then 7 is attached to 4, this is 4, and 4 is attached to 5, this is 5, and then 5 is attached to 6, this is 6. So this is how these two structures, they are equivalent structures. And then uh, this carbocation will change by breaking of this bond, 4 and 5 bond. This bond breaks, and this will form a bond at 3 and 5. 4 and 5 carbon bond will break, and this will create a new bond at 3 and 5. So 3 and 5 is formed, 4 and 5 is broken, and that means when this electron pair goes to this place to form a bond, that means this 4 will now have a carbocation. So basically 1 to methylene shift has taken place from here to here. So that is why this is a Wagner Meerwein shift, and the rearrangement is Wagner Meerwein rearrangement. So this carbocation then again will react with the nucleophile, and we will get isobornyl chloride as the product. So the difference between the two reactions which we have seen, this one and the previous slide, there we have used alpha pinene, and that was converted into bornyl chloride, and camphene, which is isomer of pinene, has been converted into an isomer of bornyl chloride, that is isobornyl chloride, and both the reaction they have undergone Wagner Meerwein rearrangement. The next example is isoborneol. This is an alcohol, again a natural product. If this is reacted under acidic conditions, this will be converted into camphene as the product. So how the reaction takes place? So when first step will take place, when H ions they are added to any alcohol, we know that this will be protonated, and we will have OH2 positive over here. That means this will lose a molecule of water, and a carbocation will be created at this carbon. So this is the structure formed by adding one proton and removal of a water molecule. We will get this type of carbocation, and then this carbocation is formed. Then this bond 1,6 bond breaks, and this moves to position 2, and we will get this type of carbocation. So 1 to methylene shift has taken place, 1 to alkyl shift has taken place to give us a more stable carbocation. You can see over here, this was a secondary carbocation, and now we are having a primary carbocation, tertiary carbocation, which is more stable than this one. And this carbocation is having equivalent structure of this one. You can see over here, only thing what I have done is that this has gone upside, this has become downside, and this has moved to other side. So you can see from the numbers that this one is number 1, where methyl group is attached, and adjacent to 1 is 7 with 2 methyl groups, and 7 is uh, joined to 4. This is 4, and 4 is joined to 3. This will become upside 3, and 3 is joined to 2, and 2 is joined to 6 and 5. 2 is joined to 6 and 5. This will go to this side, this will go upside, this will go downside. So this is how this will change into this structure, and both these structures, they are equivalent structures. And then H positive will be eliminated from this carbon, and we will create a carbon-carbon double bond at this place, and this is the structure of camphene. So this is how a rearrangement of methylene group, shift of a methylene group will change from secondary carbonium ion to a more stable tertiary carbonium ion, and which on losing proton will change into camphene. So this is how isoborneol will be converted into camphene through Wagner Meerwein rearrangement. Then stability of carbocation intermediate, which we have seen in the last few examples, is not the only factor leading to these rearrangements. So these rearrangement may also occur to relieve the angle strain or torsional strain or steric crowding in the reactant structure. So to relieve any of these strains, the alkyl or aryl migration takes place. And so the second category which is there, in addition to the stability of the carbocation, the relieving of these strains also is a factor which leads to Wagner Meerwein rearrangement. So for example, ring expansion of 2-cyclobutyl propane 2-ol. So this is the structure 2-cyclobutyl propane 2-ol. When this is reacted with sulfuric acid, 5 normal sulfuric acid, then different types of products they can be formed. So one is this one and other is this one, but both the products you can see that 4-membered ring has changed into a 5-membered ring. So ring expansion has taken place, and we know that strain is more in case of cyclobutenes than in case of cyclopentenes. So they are less strained in comparison to cyclobutane. So that is why the Wagner Meerwein rearrangement has taken place. The mechanism of the reaction is same, which we have seen in the previous cases. In the first place, H positive ions from acid, they will add to the alcohol, and a molecule of water will be lost to create a carbonium ion of this type. So this type of tertiary carbonium ion has been formed. We know that tertiary carbonium ion is very stable carbonium ion, but this is attached to a 4-membered cyclic ring. So to relieve the angle strain and torsional strain, this ring will try to expand, and this will carbon-carbon bond will break from carbon 1 and carbon 2 from this place, and this will move to this carbon 5. That means when this moves to this place, the carbonium ion will be generated at carbon 1. So we will get a 5-membered ring carbonium ion like this. You can see over here, although this was a tertiary carbocation and this is a secondary carbocation, in terms of carbocation this is more stable, but to relieve the strain, torsional and angle strain of 4-membered ring to transfer into a 5-membered ring, this gives more stability to the system. So that is why this migration of 1 to methylene group takes place to give us a ring expanded product. So this carbocation then either lead to the formation of this product by reaction with water. So OH from this water will attack as a nucleophile on this carbocation, and we will get this as the product. Or 1,2-methyl shift can take place, and we will get this type of carbonium ion, and you can see that these are both the structures, they are 5-member structure. Why methyl shift has taken place? This was a secondary carbocation, and now this has changed into a tertiary carbocation which is more stable, and after that H positive is removed, and this will form a carbon carbon double bond to give us these alkenes as the product. So this is how these two products, they are formed by Wagner Meerwein rearrangement from 2-cyclobutyl propane tools. Then there are many substrates where a sequence of rearrangements they take place within the same molecule. We can see this compound here. We are having 5 cyclopropyl rings on a cyclohexyl moiety. So this is cyclohexyl alcohol with 5 cyclopropyl rings. So when this is reacted under SD conditions, like any alcohol, what will happen? This H ion will add to this, OH2 positive will be formed, and this OH2 positive will lose water molecule, and a carbocation of this type will be formed. And this carbocation will undergo 5 concerted alkyl shifts as has been shown by the arrows. So in the first place, this bond will shift to this place, and 3-membered ring will become 4-membered. So this is how all the 5, they will change into 4-membered rings, and the carbocation will move to the next carbon. So we will get this type of carbocation. Then this carbocation will react with water as a nucleophile, and OH will be placed at this carbon. So this will be the product formed by 5 concerted alkyl shifts, thereby expanding the ring size from 3-membered ring to a 4-membered ring. So basically you can see over here that the angle strain and torsional strain of 3-membered ring changes into a 4-membered ring through Wagner Meerwein rearrangement. And all these alkyl shifts, they are concerted alkyl shifts leading to ring expansion of all the cyclopropyl rings which are present in the molecule to cyclobutyl rings. So this is a very important example of Wagner Meerwein rearrangement. Then another example in the steroidal system, a triterpene 3-beta fridalenol. This 3-beta fridalenol, this changes into del 1318 oleanine by Wagner Meerwein rearrangement, and this reaction takes place by 7 successive 1-2 shifts, either hydride shift or 1-2 methyl shifts take place to give us this type of product. So basically here also what happens, the H positive ion will react with OH, and a carbonium ion will be generated at carbon 3 with the removal of water molecule. So at carbon 3, a secondary carbonium ion is generated at C3, and this formation of secondary carbonium ion will initiate the successive rearrangement. And then when this is formed at carbon 3, carbocation is formed, then one hydride from here will be shifted to this place. So the first is 1-2 hydride shift from C4 to C3. This is C4. Hydride from here is shifted to C3. That means carbonium ion will shift to carbon 4. And that will be, here it was a secondary carbonium ion, now it will be a tertiary carbonium. Then after that 1-2 methyl shift from C5 to C4. So this methyl will shift from this C5 to C4. That means now the carbocation will be at C5, and at C5 1 to hydride shift from carbon, then 1 to hydride shift from C10 to C5. So this is this carbon is adjacent to C5. Here we were having the carbocation, then this hydride will shift to the carbon 5, and now we will have a carbocation at C10. Then 1 to methyl shift will take place from C9. So we were having carbocation at 10. Now from this methyl will shift to C10, and now we will have a carbocation at C9. Then a 1 to hydride shift will take place from C8 to C9. So this is C9. We were having now carbocation at this place. This hydrogen now will shift from C8 to C9, and now we will have a carbocation at C8. Then 1 to methyl shift will take place from C14. This is C14. This methyl will shift to this carbon, and now we will have a carbocation at C14. Then this is C14. Now we are having carbocation at C14. Then this methyl from C13 will shift to C14, and that means now we will have a carbocation at C13. So a C13 we will have a tertiary carbocation, and this carbocation is stabilized by loss of proton from C18. So this is C13, and this proton is lost, and this will create a double bond at C13 and C18. So this will create a double bond at C13 and C18. So this is how this 3 beta fridylanol is converted into 1318 oleonine by 7 successive 1,2 shifts, either hydride shift or methyl shift. So this is also a very important reaction for synthesis of unsaturated triterpenes from terpenols through Wagner Meerwein rearrangement. Then few recent examples of Wagner Meerwein rearrangement. Wagner Meerwein rearrangement has been used in targeted synthesis of perhydro 3A6,4,5 diepoxy isoindoles. So what happens is the reaction of diepoxide, this is diepoxide, this is one epoxide, this is another epoxide, and these are perhydroindole derivatives. When these are reacted with boron ethride in presence of acetic anhydride, they give us these types of products, right? But these products, they are formed by Wagner Meerwein rearrangement. So what happens is in the first place BF3 ethrate that as a Lewis acid will interact with this oxygen, and this will create a positive charge on this, and this bond will be shifted to this place, right? And then acetic anhydride will add to the positively charged carbon, and then BF3 ethrate will be lost, and we will get this type of carbocation where at one carbon we will be having acetyl group which has come from this acetic anhydride. And then when this carbocation has been formed, then this will undergo a migration of this methylene or alkyl group from this position to this position. So ring expansion will take place, and we will get this type of carbocation. And this carbocation on reaction with another molecule of acetic anhydride This will act as a nucleophile and acetate group will get attached to this position and we will get these types of products. So this is how we will get the products from these types of perhydro diepoxy indole derivatives. They are converted into these types of ester indoles. Then the synthetic application of this rearrangement has been studied in steroidal epoxides also, and these steroidal epoxide also they have a tendency to undergo ring opening and isomerization through Wagner Meerwein rearrangement. So if we are having this type of epoxide and in presence of this ionic liquid at 110 degree centigrade, this is converted into this type of alpha methyl ketones. And what happens is that in case of these ionic liquids, this proton which is present on the imidazole ring is very acidic proton, and this acidic proton will attract this oxygen towards itself and form a hydrogen bond with the oxygen, and because of that a positive charge will be created at this place. This bond will break, this will get attached to the ionic liquid, and now we will be having a carbocation, and this carbocation then will rearrange to give us these types of products through ring expansion reaction. So this is how the epoxide A will afford 13 Fp 18 or 6 own derivative, this as the product. The next is the example of spiroesters. They are converted into tetrahydronaphthalene ester derivatives through Wagner Meerwein rearrangement. So here also what happens is when these types of spiroesters they are reacted under acidic conditions, they are converted into these types of tetrahydronaphthalene ester derivatives. What happens is that this alcohol functional group will interact with the acid. OH positive, OH2 positive will be formed, water will be lost, and H will be removed from here to create a carbon-carbon double bond. So first, by loss of water, carbocation is generated, then this is lost, we will get a carbon-carbon double bond, and then this bond will shift to this to undergo a ring expansion reaction. This will move to this place, this will move to this place. So then again this hydrogen will move from here to this carbocation like this. This will form a carbon oxygen double bond, this double bond will move to this place, and this 1,2 methyl shift will take place at here. And that is how these types of spiro compounds through ring expansion and 1,2 alkyl shift they are converted into these types of tetrahydronaphthalene ester derivatives. Then is Wagner Meerwein rearrangement has also been achieved in case of alkanes. So when alkanes they are treated with Lewis acids and an initiator is used in some catalytic amount only. Then these alkanes they will undergo Wagner Meerwein rearrangement, and most common example is this one, tricyclo 521026 decane in presence of anhydrous aluminum chloride is converted into this adamantane. Similarly, this type of tricyclic compound dodecahydro acynaphthalene is converted into dimethyl adamantane in presence of anhydrous aluminum chloride. And this type of tetrahydro Tetradecahydroanthracene in presence of anhydrous aluminum chloride is converted into tetramethyladamantane. So in all these reactions, a successive 1,2 or 1,3 hydride shifts or alkyl shifts takes place to give us these types of adamantanes. And the exact mechanism of these conversions are still not known, but only thing confirmed is that these types of structures, they are converted into adamantane or adamantane derivatives, and the reaction involves Wagner Meerwein rearrangements. Then some applications in organic synthesis. 9H fluorine 9-yl methanol, this one, when treated under SD condition, this is converted into uh, this type of polycyclic hydrocarbon, that is phenanthrene. And these can be very easily synthesized from these types of alcohols under acidic conditions. So again the same mechanism, H ion will add to the alcohol, a molecule of water will be lost, and CH2 positive, this type of carbocation will be formed, and this carbocation will, by breaking this bond, ring expansion will take place, and we will get a 5-membered ring will be converted into a 6-membered ring through 1,2 alkyl shift. And then H positive, which we have added at the start, will be lost at this place, and this will be aromatized to give us phenanthrenes as the product. And this is how these types of alcohols under acidic conditions, they can be converted into phenanthrene through Wagner Meerwein rearrangement. So these are the books and other references which have been used for preparing this lecture. Thank you very much.